experts because the Higgs discovery and any current physics analysis in the collider regime, it needs a lot of statistical analysis, inference, and different tools to understand the data, the significance of the discovery, etc. And Professor Kyle Cranmer is one of the core experts in this effort. So, Professor Cranmer.
Hello, thank you very much. Can you hear me okay?
Yeah, sure.
Okay, great. I'm going to share my screen now. Does that look okay?
Yes.
Can you see? Yeah, okay, great. All right, well, I will start. Yes, thank you very much for inviting me. It's really, well, it's very nice to join you today, and it's nice, putting this talk together, looking back at all the memories from, going back 20 years ago or more. So I'm going to be talking about sort of the statistical aspects. So it's a bit of a switch given Professor Virdi's talk, which is much more on the kind of hardware end of things. I'll start with just kind of a personal statement that in terms of my journey with the Higgs boson, it mainly started in around 1999 when I was entering graduate school. I moved to CERN, and I was actually working on the ALEPH experiment, which was a part of the LEP collider, prior to the Large Hadron Collider in the same tunnel. There I was, just kind of getting started, but I did get involved in some of the work on the statistical aspects of the Higgs search, but at LEP. And one thing that I think is also kind of interesting to remember is that at the time, there was actually some excess in the LEP data and quite a bit of excitement that maybe we were, discovering the Higgs boson at LEP. That turned out not to be true, but we didn't know that at the time. And there was a very interesting and very difficult decision that the director and management of CERN had to make in terms of whether or not to continue running LEP, which seemed like it was right at the cusp of discovery, but also that would have put the whole LHC schedule at risk. It would have broken all sorts of contracts and made things go over budget, and really risk the LHC happening at all. And at this point, the superconducting super collider was still, I think, fresh in everyone's mind. So there was this very difficult decision, and I think that's also a good place to start, to remember that really when you talk about statistics, and the essence of it is really about making decisions. And so it was a very difficult decision that the director of CERN was faced with, and they decided to stop running LEP and to start the LHC project. So my PhD thesis was kind of happening during this time, and I primarily worked on preparing for the Large Hadron Collider, even though it wasn't running. A lot of the work that I was involved with was trying to establish this different production mode for the Higgs called vector boson fusion, which is pretty well studied now, but at the time, the design reports for ATLAS and CMS didn't actually include vector boson fusion. So there was quite a bit of work to show that it was actually a viable process experimentally. And then I'll say, so I'll be focusing kind of on the statistical aspects. And I'll say that, on the journey from going from LEP to the time of the discovery, and the kinds of major questions and challenges that we had to face. So one is that we wanted the statistical procedure to be, as powerful as possible, so that we could, get as much out of the data as possible. We also wanted to make sure that that procedure was robust to fairly significant theoretical and experimental sources of uncertainty. We wanted to do this in some kind of well-founded formalism that didn't just look like some physicists came up with it on their own, but something that the statisticians would recognize as being, valid and well-founded. We also wanted the ability to combine multiple different channels or different searches for the Higgs, because the Higgs can decay in multiple different ways, it can be produced in multiple different ways, and you really want to bring all of this evidence together. And we also wanted to be able to streamline that process, because up until that point it had been very cumbersome, and I'll touch on that again later. And we wanted something that would be flexible enough to be able to not just answer the question of like, do we see a new particle, or not, but also transition into studying the properties of that particle, and look to see if maybe there's some hint of beyond the standard model physics. And then, of course, in the background of all of this, it needed to be sort of computationally feasible, because as you'll see, many of the things that are sort of easy to write down on a piece of paper end up being, quite challenging computationally. Okay, so I'm going to give a few preliminaries just to kind of set some language. I'm not expecting everyone to be, experts in statistics or anything, and I'm not going to go too heavy. Most of this talk is more of a retrospective and kind of storytelling, and so hopefully I have quite a few slides that are that I found from, that were slides from the day that they were given. So I thought they were kind of interesting to look at. So so I'm going to flip through some of these slides more as visuals than to text that you're expected to read or anything. So first, let me just try to engage you by thinking back to when we talk about the discovery, and we say that we've discovered a Higgs, what is the statistical statement that goes along with that? And I'll sort of put it as a kind of multiple choice type of question. If you were to try to, in your own words, say what is the meaning of the discovery in statistical language, I'm going to give you kind of a template, a sentence that's sort of the form, the probability of something given something else is either very large, close to 100%, or very small. So what do you think the statement is? It could, and so I think that, the things that I'm thinking for X and Y here would either be that, the Higgs exists or doesn't exist, and then something about the LHC data or some property of the LHC data. So, take just a moment to think about what do you think the statement is? Okay, now, if you voted for either of these two options, for instance, that the probability that the Higgs exists given the LHC data is close to 100%, that seems like a very natural statement for the statement of discovery. Symbolically, you might write it something like the probability of the Higgs, this bar reads given the LHC data is close to 100%, or the probability that there's no Higgs given the LHC data is close to 0%. These, I don't make too strong of a distinction between these two statements. That seems very natural, but then we should think about how would we actually go about calculating this number. And what you run into is that you hit something called Bayes' theorem. If you want to make a statement of the form, the probability of the Higgs given the LHC data, then through Bayes' theorem, it's going to be proportional to something that we can calculate, which is the probability of getting some data with some certain properties given the theory, like the standard model theory, once you've say specified the mass of the Higgs. So this is something we can calculate, but then it's going to be proportional to another term, which is called the prior on the theory. And unfortunately, no one is really telling us whether or not the Higgs exists or doesn't without any other data around. This is not something you can calculate from your theory. It's really just purely an assumption, right? And the whole reason we're building these detectors is because we don't know if the Higgs exists or not, right? So if we're going to include this factor at the very beginning, if we're quite sure the Higgs doesn't exist, then we're going to get something very close to 0. And if we're very sure that the Higgs does exist, we're going to get something very close to 1. So this is, for that reason, it's somewhat unsatisfying to try to, cast the question about the Higgs discovery in terms of the probability the Higgs exists given the LHC data. So instead, we want to be able to make some, slightly different statement, which is more a statement about the probability of the data given the theory. And these are very easy to mix up. And this is just a reminder that these two kinds of things are not equivalent. And a simple example would be something like, say, your theory might be whether or not someone is a professional basketball player or not, and your data might be whether they're short or tall. And the probability that someone's tall, given they're a professional basketball player, may be close to 100%, but the probability that they're a professional basketball player, given that they're tall, is probably very, very small. All right. So how do we go about then trying to calculate the thing that, this probability of data given the theory? This is the thing that is under more control as an experiment, as a physicist. So one of the basic things that we can do is just count the number of events that satisfy some criteria. So for instance, I might look through the data for all of the events that have 2 well-identified photons, maybe with some momentum above a certain threshold, and then ask that the invariant mass of those 2 photons falls in this window. So that's a property of the data, is how many events satisfy this criterion. And so we can then think about, okay, well, what's the expected number that we would have? That would be something like the area under this curve. And we're going to have 2 different, an expected number if the Higgs exists, that includes the bump, and if the Higgs doesn't exist, which would be sort of without the bump. And so that's going to be this expected number of events nu. Okay. And if you assume that all the collisions are independent and basically identical, then the distribution of the number of events that you would expect to see is given by a Poisson distribution. And here's the formula. Okay, but so if you imagine repeating the whole LHC over and over again, the number of events that you would see would fluctuate, and this is the distribution for that number. Okay, now I think a lot of times when you start talking about statistics, a lot of physicists think, okay, this isn't really physics, I'm gonna tune out. But I'd just like to remind you that, if you feel more comfortable with terms like cross sections and luminosity, that actually those terms are kind of pulled out of something more fundamental. And the real first principles thing that you calculate when you're doing, quantum mechanics or quantum field theory is well, you start off with a scattering amplitude and then you square it, and you're talking about a probability for a scattering process to happen. So really the first principles thing that you calculate is a probability. And then we sort of factorize that probability into 2 terms, a luminosity, which is related to the beam and the flux of protons, and then a cross section, which then we think of in terms of a scattering matrix element, and then a phase space factor. And so the one piece is really handled experimentally. The other part we can calculate theoretically. But when you put these 2 pieces together, you're really reassembling a probability again. And once you take that probability times the number of potential interactions, you get to something like an expected number of collisions with some property. Now, because of quantum mechanics and various things, if you look at a particular collision, you don't know if it's, say, a signal Higgs event or a background event. And so what you really need to do is model the sum of the 2 processes together. And so here, this is just kind of reminding that the expected number of signal events would be that luminosity and cross-section term times a branching ratio term of how often the Higgs particle, say, decays into the final state you're interested in, and then an efficiency term, which is how often would you actually select events like that. Okay, so that you have inefficiencies due to coverage of your detector and the reconstruction and etc. So you do that for both the signal and the background, you add those 2 together, and that's the expected number that you would see, and then you have this Poisson distribution based on that. So this is all very basic. Now this is just to tie back to the physics. These are the different production modes for the Higgs. The gluon fusion production mode was kind of primarily responsible for the discovery. The vector boson fusion one I mentioned earlier, this is one that I was working on as a graduate student. It's particularly important because this interaction of the Higgs and the W and Z bosons is really what makes the Higgs the Higgs. But here we see the cross sections as a function of the mass. This is all being predicted from theory. And then the branching ratio of how the Higgs might decay as a function of the mass. And we didn't know the mass at the time, right? So, and you can imagine them putting these 2 together into a table like this. And so each cell of this table is a different combination of production and decay mode, and they have different, challenges experimentally. And so each of these boxes really requires a team to go after and try to search for it. And some of them are essentially hopeless experimentally. Several are very promising. And we've been kind of filling out this table as time goes on. So in terms of the discovery and picture, and going back to what is the meaning of discovery, the simplest version of it is that you're just counting events. And so the horizontal axis here is the number of events. This red distribution is the distribution of that Poisson distribution you expect if you only had background. If you had signal, then you expect some more events. So you get a distribution like the blue one. In the end, you're going to observe some number of events. That's the black dotted line. And then you would, for instance, just calculate this probability, this tail probability, which is referred to as the p-value for the background only hypothesis. And basically, the idea is, the more events you see, the better, that's more discrepant. And so the smaller this probability is for the background only, the kind of more significant the excess is. And so the statement about discovery is really something about a property that of the background only hypothesis given the data, and that basically that the data are not consistent with that background only hypothesis. And we usually require that probability to be incredibly small. So something like 3 × 10⁻⁷ to claim a discovery. Now, when you flip the story and you talk about exclusions, and I won't say too much about exclusion, but the situation, again, the background only looks the same. And what you're asking yourself is how much signal can I add before the signal plus background hypothesis is inconsistent with the data. So if this was our observation, this black dotted line, a theory like this dash line would be consistent with the data. There's, this is not a very unlikely scenario. A situation like this way out here would be considered excluded. The number of events you expect to see with the signal plus background is much larger than what you observe. And then there's some critical value, and that's where you put this sort of 95% upper limit. And this 95% is not nearly as kind of conservative or stringent of a requirement as we use for discovery. Okay, so that's the simplest version if you're just counting events. But we often have much more information. We have all sorts of energies and angles for the particles that are hitting our detector, and we can take advantage of that. So here's one of the famous plots that shows the invariant mass for the four leptons system, and you see there's a very clear bump, and so you would like to use this information, and so this horizontal axis I'm calling a discriminating variable. And I'm using the letter M to describe kind of generically this horizontal axis. And so you want to use this distribution, the shape information, which is related essentially to a differential cross section. And so when you go to assemble that, you have a distribution that comes from the signal process, a distribution that comes from the background process, and then the total distribution is just a weighted sum of those two. So you have something like, here's the signal part weighted by a signal rate, a background shape weighted by a background rate, normalized. And so that is, and then if you think of all of the events as independent, you just multiply the probabilities for their probability densities for all of those. And then you also have another term in front, which was that original Poisson piece that we started with. So this would be kind of sometimes called an extended likelihood, or a statistician called a Poisson point process. But here's the equation for the sort of likelihood for the data. So, okay. So now if you go back to this picture about discovery, we need to revisit this picture because now we have more information. We have this continuous data, these discriminating variables, and we can model, we have a probability model for what it looks like, but what's going to play the equivalent of this horizontal axis now, now that we have this other information? We're not just going to count events. And we know that intuitively, one golden event with a very high signal to background ratio is going to be worth more than, maybe 2 or 3 kind of ugly, messy events with a low signal to background ratio. So a principled way of combining all of this information was adopted by at LEP and the LEP Higgs group. And so let me just back up one step before I describe it, is that when you're talking about hypothesis tests, this is kind of generically the picture. You have some sort of horizontal axis. And this is why our question is like, what is this axis? And then you have a distribution for your null hypothesis, say background only, a distribution for the alternate hypothesis, which is signal and background. You're going to have some threshold, or like you'll have the actual observed data at some point. And then you can calculate the sort of probability, false negatives, false positives, and all of these kinds of things. And what we're trying to control when we do discovery is how often we claim a discovery when there's not actually new physics. Okay, that's called a type 1 error. So this is what would be something like claiming the verdict of guilty when someone's not actually guilty. So that's what we're trying to control. And so going way back to the 1920s and 30s, NEYMAN and Pearson had formulated hypothesis tests in this way. And then they asked the question can we figure out how a principled way to talk about the region of the data where if the data falls in that region, we will claim a discovery, or we won't claim a discovery. Or similarly, we will reject the null hypothesis or we won't. And so that region is called W here. And what NEYMAN and Pearson showed was that the optimal way of doing this, like the region that has the most power, is a contour of the likelihood ratio. And so in other words, this likelihood ratio is the horizontal axis that you want to use. So this this is just a single number that quantifies what could be a very complicated experimental data set. And so here it is at LEP, this horizontal axis. It says -2 log of Q, and Q is the likelihood ratio between essentially this signal plus background hypothesis and the background only hypothesis. If you expand that out, you get to this formula when you take the log. And what's interesting is what you see is there's kind of a shift, this total number of signal events, that's kind of irrelevant. And then the important part is you end up just adding up all of the events. You're just counting the events, but weighted by this factor that looks like the log of 1 plus the signal to background ratio. And that's pretty intuitive. If the signal to background ratio is 0, then the log of 1 is 0, so that those events don't carry any weight. And the events with the high signal to background carry more weight. And so this was used at LEP, and that was quite an intellectual step forward. So what about after LEP? So that's my kind of like that's my preamble to get you all started. So while LEP had kind of established this likelihood ratio approach as being motivated, principled way to do it, and this tradition was carried on to the Tevatron and the Higgs searches there. At the time, the sort of software machinery that you needed to collect all these inputs from the different channels was very, very cumbersome to work with and very slow. And also around this time after LEP, Babar was getting started, and it was interested in B physics, but they developed a tool called ROOFIT, which was being used for very sophisticated maximum likelihood fits for B physics. And I'll come back to this a little bit later. So around this time, I was kind of still getting started as a PhD student. And one of the things that, I guess became clear, and if there's one thing that I will give myself some credit for, was that I was pretty young, and I recognized that there was going to be a challenge in the future. And that challenge was that at LEP, the statistical formalism was like pretty well established, but because there were very small theoretical uncertainties, because it was a lepton collider, and also it was very clean, so there were small experimental uncertainties, essentially the whole machinery for dealing with uncertainties was not very well developed at that point. If you had a very, very clear, clean, signal and background hypothesis, we knew what to do. But once you started adding, the complexities of a hadron environment, we were not very well prepared. And so that, kind of led to quite a bit of work trying to establish like statistical procedures for the Large Hadron Collider. So let's say we go back to this very simple case where we expect, say, 100 background events, and maybe we even observe 150 events. So normally this would be kind of the canonical 5 sigma type of discovery. But let's say that we have like 10% uncertainty in the background. Well, now we need to get to like, well, how do we even model that? What do we mean? And the kind of, straightforward, intuitive thing to do is to say, okay, well, I know I have this Poisson distribution for some amount of background, and then I'll just say I have like a Gaussian to describe my uncertain background rate. It's centered at 100, it has a width of 10%, and then I'll just kind of integrate or do a convolution or smear these two things together, and that will give me a new distribution for the number of events I expect, as a function of how much signal I stick in. And so this would be, the red was kind of schematically the background hypothesis. So that seems very intuitive, and that was kind of what was done at the time. But what a few people realized was that this procedure is actually Bayesian again. And if you want to be like really rigorous, we were kind of mixing two different ways of thinking about probability, and it's not really clear what this equation means. And so basically, while the background uncertainty is uncertain, while the background rate is uncertain, it's not really random in the same sense as the number of collisions is random. So then you can ask yourself, okay, well, what do I mean by I have a 10% background uncertainty? Where does that come from? And it could come from several different sources, but one very well-founded way would be, say, that you have a sideband. So you're trying to count the number of events inside of a signal region or like a mass window, but the background rate here is informed by the number of events in the sideband regions, right? Of course, the number of events in the sideband regions is also fluctuating, so you don't know it exactly. But if you get to a situation like that, then you might say, okay, well, this distribution of the background I can think of as essentially a posterior distribution of the background given the number of events in the sideband region, which I'm calling N off. And if you use Bayes' theorem again, you get this formula. But what you see is that it requires, again, a prior probability on what you think the background rate is in the first place. And you can't get away from that. So, so if you want to not have that dependence, then you need to basically just try to model the signal and the background region simultaneously. Then you don't need any priors. And that's where you start getting this joint model where you have a Poisson distribution for the signal region and the sideband region. And they're mathematically connected in some way in the sense that the background rate on the sideband is tied to the background rate in the signal region by some multiplicative factor here called tau. Okay, so that was kind of just the basic conceptual step forward. But you have to be able to handle much more complicated situations than this, just simply counting events in signal and sideband regions. So I will acknowledge Louis Lyons. I was a young graduate student. Louis Lyons, who was organizing the PhiStat conference, suggested that I sort of study this problem. It led me to kind of a long path, but one of them was to realize that there was this generalization of the likelihood ratio called the profile likelihood ratio. I'll just say a little bit about that. But before we do that, I need to introduce this notion of nuisance parameters. Okay, so this is basically what I showed before. If you have a data set that has a bunch of, I called it M before, now it's called X, I apologize. So X is the discriminating variable, like the invariant mass of your, and N here is the number of observations that you have, number of events that were selected. So you have a Poisson term that counts events, and then you have some shape information. But here there's no freedom. That statistical model, like the shape is just totally fixed. Once you have uncertainty, you have to realize that, okay, I don't know the actual normalization perfectly, and the distribution has some uncertainty associated to it. And so what you need to do is parametrize what that distribution might look like. So the number of events new is no longer just a number, it's a function of some parameters. And those can be functions of things like the electron energy scale uncertainty, or the uncertain cross-section of the Higgs production, or the uncertain luminosity of the detector, etc. And that also the distributions are not fixed distributions, they have some uncertainty to them. And again, that might have to do with energy scale uncertainties and various things like that. And we separate the parameters into kind of two different groups. There are the parameters of interest, here called mu, and those are the things we actually want to measure. So things tied to like the mass of the Higgs, the cross-section and branching ratios, those kinds of quantities. And then we have a lot of nuisance parameters, which would be things like energy scale uncertainties or luminosity uncertainties and things like that. Okay, so now we have this statistical model that has a lot of parameters that you might stick into a fit. And so the idea here is that this profile likelihood ratio is again a likelihood ratio, but what you have to do, you have to specify what the value of these nuisance parameters are in the numerator and the denominator of this ratio. And so what you do essentially is in the numerator, you do a fit to the model, but you don't let the parameters of interest float in the fit. You fix them to some value, and in the denominator, you let everything float. And so so here it is in pictures. Here's the best fit for this kind of toy data set where you let this is a Higgs to tau vector boson fusion example, but you let everything float in the fit, and the black curve is the best fit model. And here is the best fit model when you don't allow there to be any signal, but so the background is going to try to adjust to accommodate the data. And then you ask yourself, okay, well, how much better of a fit is the one on the left than the one on the right? That's what this likelihood ratio is telling you. And so it's fairly intuitive, but it wasn't something we were doing at the time. And if you look at this formula, there's a few things about it that are important. One of it is that you have eliminated the dependence on the nuisance parameters. The function only depends on the parameter of interest. And then the thing that's also interesting is there's a theorem called Wilks' theorem that says the distribution of whatever -2 times the log of this likelihood ratio looks like a chi-square distribution or something closely related. And which is very useful because it means you can calculate these p-values and things without having to do a lot of Monte Carlo. So this was happening around 2008 that we or 2007ish that we realized this, and we were took us a while to kind of work through it all. But you know,
Kyle?
yes.
Yeah, could you please define what is G?
I'm sorry.
Previous slides.
Yeah, could I define which?
G.
Oh yeah, sorry. Yeah, D here was meant to be the
Discriminator G.
yeah, D was meant to be the kind of all of the data here, and I'm sorry, I did kind of skip. So the main data, the data here, script D is meant to be the main kind of signal events that you're interested in, so like the invariant masses and etc. And G, yeah, I apologize, I didn't describe it here. G is meant to be all of the kind of auxiliary measurements that you used for like energy scale uncertainties and you know, cross sections and sideband measurements, all the kinds of things that are kind of not your main signal, that where you have the kind of, when you say that you have, say, a 5% uncertainty in your jet energy scale or something like that, G is sort of representing all of those measurements. Yeah, I apologize. Yeah, thank you.
Kyle?
Yes.
Yeah, in this expression, you are not assuming any like condition on mu hat in relation to mu, right? Mu should be less than mu hat.
Yeah. So there are, yeah, I didn't get into for this talk, I didn't get into the kind of some of the additional complications. So I talk about how, yeah, the more complicated if you have boundaries and things. So in the initial formula here, this would be like if you wanted to make a sort of two-sided measurement of the quantity mu. So like, say you want to measure the mass of the particle and you want to have a central value and then sort of two-sided errors. When we talk about discovery, we're really only interested in fluctuations that are on the positive side, right? You know, that we have more events than expected. And when we're doing limits, we really only care about fluctuations that are on sort of on the negative side, where we have fewer events than expected. So this is the core idea of this profile likelihood ratio, but then in the different contexts, you might put some other like requirements, like that mu is larger than the best fit value and things like that. So that's absolutely true, and it does lead to some complications, but I didn't get into that for this talk. Okay, so I will say that at this point, when we first started thinking about these things about like frequentist background uncertainty, you know, you get into lots of debates, and it was like, okay, you get into debates about the sort of principles and like, you know, which the merits of the different approaches. And so one of the things that you know, realized at the time was like, okay, well, instead of making it a sort of philosophical or aesthetic argument, why don't we just look to see how often different procedures will claim a false discovery? And what I found at the time was that if you had sort of 10% uncertainty and say order 100 background events, which was definitely an example that you would see at the LHC, that some of the procedures that had been used up until that point, what they would claim to be 5 sigma would really be more like 4 sigma. So the rate at which they were, you know, claiming discoveries too often would be, you know, factors of hundreds or thousands of times more than you wanted. And so that, you know, basically was seen as a problem and was like the motivation for like doing something better. This is a paper from Bob Cousins and his student at the time, Jordan Tucker, that you know, kind of studied more systematically how severe this problem was. But it was recognized that something kind of needed to be done. So that was, I guess, you know, around 2005 that became a little bit more clear to the community. And right around that time, Renee Brun, who was the head of the lead for the Root software package, approached me and asked me if I would think about like putting together some kind of statistical framework inside of Root, and also suggested that I look at ROOFIT, which had been developed at Babar and had started to be part of Root. And so at that point, there were various statistical tools in Root, but they were kind of very ad hoc and not like unified. So these are some slides from 2007 at a Root workshop that I just thought was kind of interesting. Here is like, in addition to providing, you know, cool tools for simple calculations, we need to be able to combine results, incorporate systematic uncertainty, facilitate the technical aspects of sharing code and the different, you know, stuff for doing the combination. Talked about how LEP and Tevatron had some machinery for doing it, but it was basically very, you know, kind of a little bit too cumbersome and not very flexible. And that we really wanted some kind of statistical framework that would allow us to do either Bayesian or frequentist type statistics or likelihood-based statistics. And it should be fairly easy to switch between them, things like this. So here you see the probability of data given theory and probability of theory given data. So these were things we were thinking about in 2007. And this is a little side picture that, because I'm going to show some figures like this later, these kind of graphs. So let me just give a really simple example. If I wanted to talk about a Gaussian distribution for the variable x, that Gaussian distribution has a mean and a standard deviation. And so I'll make a little graph that looks like this, where once you specify, the value of x and the value of the mean and the value of sigma, then I can calculate the probability density G, for the Gaussian distribution. But these can start to be more complicated diagrams. So ROOFIT was like a modeling language that allowed you to, piece together something more complicated. So for instance, you could add distributions together or multiply them. You could do convolutions and things like this. And the way it composed these building blocks, it made these kinds of graphs like I'm showing. And they could be kind of, arbitrarily complicated. And so we started to use that as the basis. Also, ROOFIT, had a connection to MINUI, so you could do all the fits you needed for the profile likelihood ratio. And then in around 2007, we realized that we could use the underlying technology of root to be able to take whatever a physicist might assemble in their piece of code, and then just write it to a file, which you could then email someone, and then open up that email, load up root, read the file, and then there you would have the statistical model, the data, and you could redo the fits, and you could do all the things that you want. So it became an incredibly useful way of sharing statistical models, and we called that thing the Workspace. And that really has just been used tremendously across the field, and it was really vital for the Higgs combination. This is sort of looking ahead into the future, but just to give you a feel, during the time of the discovery, here are plots from ATLAS. We had to combine all these different searches together. And this is a timeline going from 2009 to 2014, where you see the number of data sets that were being combined, the number of modeling components, and the number of parameters and the likelihood. And you see it's kind of grows exponentially, going from just one or two to 240 different data sets in the combination. The number of modeling components up to about 80,000, and the number of parameters and the likelihood going from just tens to 800 or so, and these have continued to grow. So so basically adding this workspace capability just led to the groups being able to work in a much more decoupled and kind of distributed way, and it allowed everyone to contribute, bring in their piece of the puzzle. And so it lowered the threshold for a contribution. Before, the threshold was so high that really only the flagship measurements would be included, and this allowed really used to many more pieces of information to be included. Okay, so then as this new statistical formalism was sort of coming about, we needed to kind of try it out and kick the wheels. And the first place that we did that was actually the kind of rediscovery of the top quark. So this was a plot, this is with 3 inverse picobarns of data, which is a kind of laughably small amount of data now. And so this, we were measuring the cross section, but we also were discovering, quote, rediscovering the top quark. And here you see the distribution of this, profile likelihood ratio for the background only and signal plus background. And this histogram is being made by doing a ridiculous amount of toy Monte Carlo. So there's tens of millions of toy Monte Carlo events. For each one, you have to redo this fit, and then you get one value, which is the profile likelihood ratio, and you histogram it, and you just do that over and over again. So this was really the first time I think that was done. Another thing that happened around this time, but it took a little bit longer before it was really established at the same level, was what I call the Asimov paper. We had been working for a while trying to understand this profile likelihood ratio better, deal with these issues that were brought up earlier about if you have, if you only consider upward fluctuations or downward fluctuations, or if you have a restriction that the signal strength can't be negative and things like this. And we worked out basically what the distribution of this test statistic, this profile likelihood ratio, should be under those different circumstances. And what's nice is that you just have an analytic formula for what the distribution should be, and you don't need to use hundreds of thousands of CPU hours to generate all these toy Monte Carlo events. So here are just some plots from that paper showing how well it worked. The histograms are from a bunch of toy Monte Carlo, and the curves are the predictions. And there's no fit here. There's no free parameters. It's just like, this is what the distribution should look like. And you see it works incredibly well. So that was pretty exciting, but it wasn't sort of fully, it took some convincing. It took about 2 years of convincing before people stopped, doing all the toy Monte Carlo. So that takes me to about, to 2010-ish. And so I'll talk about the ATLAS and CMS Statistics Committee and the combination group. So these are slides taken from a talk in 2011. But basically that ATLAS and CMS groups kind of got together. We went through a toy exercise of doing a combination. We focused on Higgs to WW with 0 jets. We were using this RooStats. We were thinking about the different kind of test statistics, profile likelihood ratio. None of this stuff was like accepted yet. Here's like a timeline from kind of May through July of 2010. It was pretty exciting. Here is the first one of the times that we combined the ATLAS statistical model is this part of the graph over here. The CMS part is over here. You see the diversity and how the different approaches to modeling the data between the two groups. It looks quite different. There's an underlying parameter of interest, which is we call the signal strength, which is just the cross section times the branching ratio divided by the standard model value. So 1 is the standard model, 0 is no signal. Yeah, at this point we had about 12 observations, about 50 parameters in the model, and it started to work. You see this, good luck to the LHC Higgs combination group in 2011. I think that's pretty cool. It's fun to see these things. We at this point had kind of like the procedure that was going to be used for the ATLAS and CMS Higgs groups had basically been established. We did end up deciding to use this profile likelihood ratio. These kinds of plots became kind of standard. And then, so I'll go to like sort of July 2011. I'll say on a personal note, my daughter was born right around that time, and I was not supposed to travel. And I told my wife, like, I won't travel unless it looks like we're going to discover the Higgs. And they asked me to give the talk. And then they asked me to give this combination talk at EPS, and it looked like we were maybe starting to see a discovery. So I did. My wife, I saw my daughter born, but then I did go to Paris, and so yeah. So this was the talk at the time. You see the different channels that were included. Even one production and decay mode might be subdivided into multiple different channels depending on if you have, say, electrons or muons or 1 or 2 jets, etc. And so at the time we were seeing there was a lot of attention over here at 140, 2 GeV, but that turned out to be a fluke. But this was the first time we were really starting to exclude regions of the Higgs, the standard model Higgs mass range. All of the kind of machinery was starting to get used. It was a very exciting time. 1 month later, I was supposed to give my tenure colloquium at NYU. It was a bit embarrassing because we had doubled the amount of data, and then that bump that we were seeing had gone away. Okay, but at that point we were here. You see these are limits, upper limits, and so whenever the solid curve goes below 1, you're excluding the standard model Higgs at that mass. So we had gone from saying nothing about the standard model Higgs to starting to exclude a lot of the standard model Higgs space. And then the ATLAS and CMS group actually got together and did a combination with real data at that point. And that, just to give you a feel, it was like 300,000 CPU hours to do that combination, because at that point that this asymptotic stuff wasn't being sort of standard yet. And then by the time we got to December 2011, things were getting like really, really serious. The combination got significantly more complicated. Here you see some of the cross checks from the time. I think probably many people remember that in December 2011, the peak at 125 was starting to get pretty sizable. And for a lot of people, they had already kind of decided we were discovering the Higgs, but certainly wasn't official. And here's a slide that I just found from January 2012 with the quote, will 2012 be the year of the Higgs? It was a pretty exciting time. I'll say that then as we entered 2012, we were actually still working on writing the paper for the December 2011 combination. So interestingly, that paper was submitted to the archive on July 2nd. So if you remember, July 4th was the discovery. Up until like, 2 days before, we were still like, putting the bow on the council chamber results. So it was a very busy and hectic time. I remember it fondly. And one personal memory, which I will always remember, is that, and it's documented in this New York Times article, but on my birthday, June 25th, my PhD student who was helping with the, well, more than helping, was doing the combination stuff. He, as far as I know, was the first person to put together the ATLAS Higgs to 4 lepton and 2 photon and see that we were going to cross the 5 sigma threshold. So, between June 25th and July 4th was not a lot of time. And so, yeah, it was very exciting. I don't know, great memories. And so then, on July 4th, I think everyone's seen this plot many times. So here was the ATLAS peak. We were all very, very excited, obviously. Here's the same plot from CMS, but with a kind of weighting procedure that, makes the peak more pronounced. Yeah, I think we all know this very well. Beautiful candidates from CMS. Here's a 4 lepton candidate from ATLAS at the time. Here's the 4 lepton plots that were shown. Yeah, again for CMS. But there was much more to the story than just 2 photons and 4 leptons. This is just kind of a reminder of all the different channels that were going in. As I mentioned before, yeah.
Yeah, so is 5 minutes okay?
Yeah, I'll wrap up. Yeah. So this was like kind of a graph of the big, statistical combination at the time. So you see it's very, very complicated beast. I already kind of showed how many components were going into this. So that was where we were. And then these are some slides that I just showed from still in July 2012. That sort of, this was at Aspen, as the discovery came in. This was, even before the discovery paper had been written. And what, we had the first mass measurements, the first measurements of simultaneous measurements of the mass and the signal strength. And then what I think is pretty interesting, is worth, saying, is that at the time, the focus was on discovery, but right after the discovery, you want to start to measure the properties of this particle. And, conceptually, maybe it's kind of clear what you want to do, but technically, it's a very different beast to be able to start to change cross sections and branching ratios and things like that, and to have those handles. And so one of the things that I think was excellent is that the ROOFIT RooStats framework was flexible enough that allowed us to switch to that mode very, very quickly. And so, almost immediately we were doing the first round of coupling measurements. So this was a plot, and still in July 2012 was like, okay, well, it'd be nice to really measure in this plane the sort of signal strength in the gluon fusion production mode and the vector boson fusion production mode, because there's a lot of crosstalk between them, lots of correlations and things like that, and you'd like to do that like in a really statistically precise way. And a month later in the discovery paper, we had that plot, and so I think that's pretty impressive. And this is really telling you kind of directly if you see vector boson fusion or not, which is very, very important for establishing that it's actually the Higgs boson and not just some other scalar particle. So 2013 was really when we moved into like more serious coupling measurements. We had started to fill out this table quite a bit. Here's, again, you see that same plot as before, with the kind of signal strength, and the horizontal axis is sort of gluon fusion and the vertical axis is vector boson fusion. You see the different colors are different decay modes. So that was pretty exciting. The slope in this line is basically telling you the ratio of vector boson fusion to gluon fusion. And so as long as this slope is positive, then you're saying, yes, vector boson fusion is happening. And so in that sense, the angle is the parameter of interest and the radius is like a nuisance parameter. And so you can profile that radius, and that's what's happening here in this plot, is you're just measuring the angle. And so in that point, we had 3 sigma evidence for vector boson fusion. You can do the vice versa. You can measure the radius, which gives you things like the ratio of branching ratios. These were all very model independent types of measurements. And then there were more model dependent types of approaches where you would reparametrize, and you would say, I think I know what the cross sections and branching ratio should be as a function of some new physics parameters. And the first version of this was to modify the couplings of the Higgs with like the top quark or the W. There are different approaches for how to do this, and whether or not you assume that there's no new physics or like new particles in the loops and things like this. So I won't go into that too much. This was one of the plots that was pretty exciting at the time, which was essentially probing if there might be new physics in the loop with the Higgs and the photons or Higgs and the gluons. And the standard model was this blue dot, and the best fit observation was over here, the X. And so there was a fair amount of tension early on, and there was a lot of excitement that maybe we were seeing beyond the standard model physics. Unfortunately, that tension has subsided, and we're now very consistent with the standard model. And then this last couple things is just to take us to today. That was all 10 years ago, and some of that goes back even longer. So 20 years ago, there were this first PhiStat meeting where we were saying, what we should really do is publish our statistical models. And while people agreed that we should do it, we technically didn't have a way to do it. Then 10 years later, that when the Higgs was happening, you had plots like this, probing if it's the standard model or not. And when theorists would try to take the information in our published papers, they would not be able to reproduce the results, and that was a problem. So we pushed to try to start publishing likelihoods associated to the different production and decay modes. So this was an early example, right, in 2013. Once you had those, then you could take those ingredients and actually reinterpret and actually reproduce the results in the papers like exactly, which was very exciting. But it still wasn't really the full statistical model, so they had limited capabilities. And if you fast forward to sort of today, this is January 2020, the ATLAS experiment has now started actually publishing the full statistical models mainly for BSM searches, but hopefully Higgs will come soon, and publishing them onto HEP data. And that I think is really, really exciting development. The other big development that's happening now is the use of machine learning. In the first round of couplings, part of why we could do it so quickly is that when you change those parameters, all you were doing were changing cross sections and branching ratios. It didn't change the kinematics at all. And so then you can just reparametrize the different components and you can do everything you need. Now we're moving to trying to study BSM physics in the context of what's called effective field theory. And that's a kind of very nice, generic, well-founded, theoretical way of talking about beyond the standard model physics. But it's more difficult to work with because it actually changes the distributions, and that requires more work than you can do just with these likelihood components. And also the signal is no longer just like a simple bump. It's distributed in a lot of correlations and angular distributions and things like that. And so what we're using now are machine learning techniques to essentially learn how to model the likelihood with a very high dimensional observation. And once we model that, we can still stick it into the same machinery that I just described to you. And so you see, for instance, we might consider these types of higher dimensional operators that are modifying the Higgs interactions. And we can work with very high dimensional data. And you can compare that to the kind of approach up until now, which is to use what are called simplified template cross sections, essentially to do number counting essentially in many different regions of phase space. And what you see is that, so here in this plot, 0, 0 is the standard model, and anything away from that is beyond the standard model physics. And the simplified template cross-section approach gives you constraints that look like the red dashed line. And using these machine learning techniques, we get to the blue oval. And so that's like a substantial improvement and sensitivity. And that's one of the areas I'm very excited about. Okay, so I will end there and just say that it was really a tremendous time. I'm very happy that we're having this celebration of what happened 10 years ago. I consider the discovery of the Higgs to be a triumph for humanity, something that we shared across the world and something that we will remember for decades, centuries, and millennia to come. And then to reinforce this point that studying the Higgs particle is really one of our best paths to uncovering physics beyond the standard model. And with that, I'll end. Thank you.
Thank you, Professor Kyle, for your very nice talk. And I must admit that his energy and enthusiasm is very infective. So now let us take a few questions. Please raise your hand so that, okay. So I see one hand already raised. So Arno, please go ahead.
Hello. Can you hear me?
Yes, I can.
Yes.
Okay, thank you. So I have two questions. First of all, one is related to the combination that the region where we are going to. So we are trying to combine multiple channels and experiments, and while doing that, actually, the number of parameters are increasing enormously. And the models are becoming large and large. And it's getting difficult these days to do a fit of these so large models. So what, I have two questions. How do you think we should approach this problem of the time that it takes or the computing power that it takes? I mean, is it going towards like using GPUs, or it is also towards the place where we are trying to reduce the number of parameters depending on the impact of them on our observable, the parameter of interest, let's say?
Yeah, no, that's an excellent question. So I think, so it's definitely something I've thought a lot about. So I think on one side, you know, when we added this technology and it led to this kind of exponential rise in complexity, in some sense it's great because you get so many more contributions and it reflects more the real complexity of the search for the Higgs. And so in some sense, I think adding this, you know, adding more and more information and details, it seems like it should only be better, right? At the same time, you know, computationally, it's much more complicated. And it is true that many of the, you know, parameters, the nuisance parameters you add really make almost no difference whatsoever.
Yeah.
But it kind of depends on which question you ask. And so I feel like, you know, there's, the principle that drives me is that you shouldn't start simplifying your modeling because computationally or technically you're not equipped to do it unless you have to, you know, that you should be able to put all the complexity in there, and then you should, you know, adapt the complexity through some other means. So, so the first thing is that once we moved to using these the asymptotic distributions, we no longer had to generate tons and tons of toy Monte Carlo. So that made just an enormous difference. So instead of doing tens of millions of fits, you're doing like one fit. But now even doing one fit, you know, has started to become very, very complicated. So in this, again, here you see sort of, you know, 600 parameters, they've gotten into the thousands. But one of the interesting things that happened here is that in machine learning, you have something very similar. You have a function, which is essentially the likelihood function, and the number of parameters of a neural network can be in the, you know, tens, well, you know, it was billions, and then they started to be in the billions recently. So, and they're still optimized through gradient descent, which is essentially what MiniWi is doing when you do a fit. So somehow machine learning has some, has developed tools and techniques and computational tools that allow you to do fits with millions or billions of parameters. And so and some of that is about GPUs, but a lot of it has to do with a technique that's called automatic differentiation, which is that if you want to, you know, when you want to know which way is downhill, and MiniWi, what it does is it evaluates, you know, that and then lots of other directions. You don't need to do that. You don't need to evaluate derivatives through finite differences. You can use this technique called, you know, backpropagation or automatic differentiation. And so the newer tools that we've developed, so I mentioned this PyHF tool. So part of it is that it allows us, it has a simpler model for publishing the statistical model, which is just a text file that you can stick on HEP data, but it also uses the machine learning frameworks to be able to use GPUs, to use automatic differentiation, and the time it takes for some fits have gone, you know, in some cases it's many hours, goes down to like 2 minutes. And there are times you can do hundreds and hundreds of fits in like a couple minutes, where one fit used to take hours. So that's part of the answer, I think.
Okay, thank you. I mean, I did some hands-on on PyHF. Actually, it's really great. But probably CMS, it will be more and more common in coming days to use PyHF.
Yeah,
but
that's great.
Now, and the next question that I had is like in your slides. I mean, though the formula is really standard, which is the profile likelihood ratio, the definition that you had, where you had this in the denominator can be different, right? So there were multiple choices that were there. I mean, like if you want to fix the mu to 0, or if you want to do a full fit, I mean, mu hat, theta hat in the denominator. So actually, I mean, I would have liked if in the last part of your talk would be more elaborate, like using machine learning for the likelihood and etc. I mean, thinking about other definitions of this likelihood ratio or whatever that makes this null hypothesis and the alternate hypothesis more distinguishable, and that will actually make them farther apart so that we can easily say, I mean, if it is a discovery or not. And do you think, I mean, the machine learning is the next choice, of course, but profile likelihood ratio is the best choice for distinguishing between the null and the alternate hypothesis?
Yeah, I'd say that, I mean, okay, there are some subtleties about whether or not you want to, consider, upward and downward fluctuations and things like that. But those are, I think, fairly straightforward. Like, but once other than that kind of caveat, which doesn't really change this too much, it's just that you kind of only consider, one side of the fluctuations. The likelihood ratio basically, there's essentially a theorem that's the best you can do. The problem with it is that the actual probability density, the likelihood itself, is not something you can kind of calculate because we have a detector in the way, right? So the way that we estimate the likelihood is using histograms.
Yeah.
We have full simulation, we use histograms, but we can only histogram kind of one or two variables at a time. So our likelihoods are restricted to kind of only one or two observables. And so if you could have more, if you could do a multivariate or like a fully differential approach, you would have more power. And that has nothing to do really with the likelihood ratio. It has to do with the likelihood of what, So you still have some choice about what you model. And so the problem there is that you can't fill histograms and like high dimensions. And so what machine learning is allowing us to do is basically model the likelihood or the likelihood ratio when you're working with higher dimensional data. So the likelihood ratio itself is still kind of preserved as the target, but you're working with higher dimensional data. And so that's where machine learning is really helpful.
Okay, thank you.
Okay, so let us move to another question. So Kajuri, Professor Kajuri Bojumdar.
Hello, Kyle. Great talk.
Hi there. Thank you.
I wanted to know briefly, when exactly should we use Feldman-Cousins ranges?
Yeah. So there was a question about, well, the question is, when should we use this approach called Feldman-Cousins? So Feldman-Cousins is, it's often talked about when we're not just talking about discovery, but you're wanting to put a limit on some parameter. Okay, so let me go actually to, let me find a representative plot. Yeah, so if you look, say at this bottom plot right here, the horizontal axis was the mass, the vertical axis was the signal strength parameter. And so, when you're talking about discovery, you're just asking like, is the rate 0 or not, right? And so you're only interested in kind of upward fluctuations. When you're doing when you're doing limits, you're asking the opposite question. But once you see something, you would kind of like to say, there's the value for like the signal strength, say like 1.5 plus or minus something, or say that it's in some range. And then you're doing this kind of two-sided interval, confidence interval, where you say, I think the value is between here and here. And what Feldman and Cousins realized was that if you kind of switch from, if you do the kind of typical thing where it's like, okay, now that we see a discovery, we're going to start making a measurement. If you do that, that's called a flip-flopping procedure, and it has some kind of problems. And so they introduced this sort of unified method that kind of smoothly goes from setting upper limits to setting two-sided limits. And so that's useful. And the way that it is based on is actually a likelihood ratio. So it would be, you would still use this kind of likelihood ratio. And one of the things that, where I kind of stepped in and started to take over from not take over, but like extend what Feldman and Cousins had done, is that Feldman and Cousins didn't know how to deal with systematics. And so when we introduced the profile likelihood ratio, it's kind of the logical extension of Feldman Cousins to including systematic effects. But you still kind of have a decision that you want to make if you want to, do this kind of two-sided unified thing, or if you want to squeeze out a little bit more discovery power by saying you're only looking for, you know, upward fluctuations. So it doesn't make a huge amount of difference, I would say. But then what happened a little bit later, which is also the same kind of issue, is when we start getting into coupling measurements. At that point, it's not like there's just a single signal strength parameter, which is like 0 or it gets, you know, bigger. Sorry, at that point, you're talking about, like, even in this plot, you have two parameters of interest, the mass and the signal strength. So there's not like a sense of upward fluctuation doesn't mean anything anymore. And so now you're kind of fundamentally in, like, there's a best fit point and then there's a region around it that's acceptable. So this really is a Feldman-Cousins kind of plot. And as well as a plot like this. This really is Feldman-Cousins, but extended to be able to incorporate systematics.
Thank you.
Thank you.
Okay, so Ramakrishna, could we have a quick question from Ramakrishna?
Kyle, I have a question about this asymptotic limits versus toy-based full CLS limits. So in Higgs analysis, generally we optimize our analysis on the basis of asymptotic expected limits. And then in the final round before, let's say, the publication, we are told to compute the toy-based limits and then see if they are close enough to the asymptotic limits or not. So in case of a discrepancy, then what should this indicate? Are we, haven't we thrown enough toys, or is there a genuine effect in the analysis that the toy-based and asymptotic limits are not overlapping?
Yeah, no, that's a good question. So the statement, you know, so it's kind of, there's two parts to it. One is like, what does asymptotic mean? So, you know, the asymptotic part basically means that you don't have to assume that, you know, the things that you're modeling look like Gaussians or anything. You know, I mean, you saw all those plots, nothing looks like a Gaussian. All the distributions are kind of complicated looking. But you need a large number of events in the data before the distribution of this test statistic starts to look like, you know, what you expect from the asymptotic formula. And so in these plots, you see the asymptotic formula and the toys agree very, very well. If you only have like one or two events expected in the data, then the distribution hasn't, you know, converged to the asymptotic limit yet. And so especially in searches for like beyond the standard model of physics, it's important to still do the toy Monte Carlo approach to check. But if you're in a situation where you have quite a few events, essentially the asymptotic stuff should work unless there are a few caveats that have to be satisfied, and if they're not, then things can go wrong. But generally, it should work. And what we found, you know, in those sort of 2 years, I would say, in kind of 2010, 11, and 12, when we continued doing all of the toy Monte Carlo and the asymptotics, is that whenever there was a deviation, it usually had to do with problems with the toy Monte Carlo, and that the fits would fail some reason or another. And most of the problems and most of the discrepancies were really some numerical problem somewhere. It wasn't about the asymptotics. And when we fixed those, then things agreed. So in that sense, the asymptotics are kind of more robust, but you have to be in this asymptotic regime. But the asymptotic regime often kicks in with like sort of 10-ish events. So you don't need a lot of events before you're there. But yeah, I do agree that, you know, if you have the computing power, and especially if you're in a low count regime, you should still do the toys.
Thanks.
Okay, I think we had a very long session, more than 3.5 hours, and still Professor Kyle's excitement and the way he introduced a very difficult subject to all of us is really nice. So let us thank him once more, and thank the other two speakers of this session. And thank you all for attending this session. So over to Kajuri, Professor Kajuri.
Visit India sometimes.
Hi, Kyle. I have a question if you have a time.
Sure, I can hang out. Thank you all for coming and your attention.
Okay, so over to Professor Kajuri Mojumdar. I give the control over to him.
Thank you so much for making time to give this talk. You were busy with moving. I hope interaction. Thanks.
I'm sorry if that was a question for me. I couldn't.
No, it was not
yeah.
a question.
Okay.
I just said thank you so much for taking your time off for this process.
Hi, can you hear me?
I can hear you.
Hi, I have a quick question. Because I just wrote it in the chat box, but just let me read it. Actually, in
There is a lot of noise from you, Suman.
I see the question. You're asking. It says that in the HH analysis, you see that a lot of the goodness of fit plots are generally done by generating toy Monte Carlo, but using the asymptotic approach for doing limits, and if there's a specific reason for that. Yeah, so that's a good question. I'm without knowing specifically about which plots you're looking at, I will say that when you're doing limits or discovery, you're comparing two different things. You're comparing some kind of null hypothesis against an alternate, and those are like the numerator and the denominator of a likelihood ratio. And when you do a goodness of fit, you're not comparing. You have like a null hypothesis, but you don't have an alternate hypothesis. And so the quantity that you calculate when you do a goodness of fit, well, there's lots of quantities. Like when you have an alternate, there's kind of a unique choice. The likelihood ratio really is kind of the best thing to do. When you only have a null hypothesis, it's not clear what to do. There's no notion of like a best test statistic for a goodness of fit. So people choose lots of different things. And so, and also because of that, you often don't have this, there's not necessarily like an asymptotic equivalent there. And there are some examples where you kind of know what the distribution of this goodness of fit test statistic is, but like it depends on which one you're doing. And so I think probably if it's again, I don't know which plots you're seeing, but it may just be that people don't know what the distribution is for, the horizontal axis, the test statistic they're using for that goodness of fit test. And so you have to use toy Monte Carlo.
In the horizontal axis, it is basically the normalized test statistic.
Yeah. So I don't normalize. Yeah, I don't know which test statistic. There's lots of test statistics out there. So it could be. I would need to see some more details. Okay. Yeah, I'm sorry. Yeah, I mean, if it is a profile likelihood ratio, I don't really know why. Unless
profile likelihood ratio, yes.
Okay, then yeah, then I'm not really sure why. Sorry, not very useful.
Generally, like in Higgs analysis or Higgs analysis in general, we are told to do like asymptotic limits till the last point, and before going for publication, we should cross-check like some important like mass points with the full CLS, and see if the asymptotic and full CLS conversion. That's it.
Yeah, I mean, I think it's always sort of it's a good good cross check. I think if you can do it, also, even if you're trying to talk, and for limits, you don't need millions and millions of toys, so it's not so bad. But sometimes you also don't need that many toys before you can start to see if the asymptotic distribution looks like it's going to fit well or not. So I think the asymptotic stuff is very helpful, but it's it's what I want to say. There's nothing wrong with doing the full-blown thing. Although if you do see a deviation, as I mentioned before, you have to ask yourself what's going wrong. And sometimes it's not the asymptotics that are wrong, it's the fitting code has problems. Yeah. Is there one more question, I believe?
Hi, Guy. This is Kapil. It's been a long time that we are talking to each other.
Yeah.
So I hope our common friend is doing well. Well, I have a question. So you talked about ROOFIT and ROOSTAT, and I haven't seen any multivariate analysis stuff like over here. I mean, did you guys employ that or not?
So you haven't seen multivariate analysis and ROOFIT and
NETMA
RooStats?
kind of discriminators and CNNs, something like that. And particularly like and these Higgs data like the BDTs like. I think in the combined plots, I think by 2012 itself, like people started using BDTs, right?
You're saying, sorry, the audio cutting out for me a little bit. You're saying you didn't see it in my talk, or you haven't seen it like.
No,
oh yeah. So yeah, no, it's certainly true that well, in the when I showed some of the slides that were, there was like Higgs to 4 leptons and Higgs to 2 photons that were simple. But then there was like the rest of the analyses, and definitely some of those, the horizontal axis there is the output of some sort of neural network or BDT or something, and certainly that was true even at the around the time of the discovery, and since then obviously there's a lot more machine learning that's been used. One thing that I will say is that a lot of the use of machine learning was originally still like a neural network that's trying to tell the difference between signal events and background events. And so once you train that neural network, you give it some data and it just gives you a number. But one of the things that we've been doing recently is a little bit different. The machine learning is not just a classifier, it's actually trying to estimate the likelihood function itself. So you give it data and you give it the values of the parameters, and it gives you back the likelihood ratio. So it's not like a one classifier. It's like a family of classifiers that depend on the parameters of interest and maybe also the nuisance parameters. So it goes.
This multiple classifiers was even there, like it exists even like at the time of 12 and 15, between that time itself is there. I just wanted to make sure that is it being used or not? So that's my question.
If the classifiers, if multivariate classifiers were used at the time of the discovery?
Yeah. That is what I'm asking. Because particularly that time, like I was mentioning about this MBA initially in the Higgs total, and then this dominant QCT background for the Higgs to BB channel, which we are all aware of. I don't know what is this current status. You should tell me what is the situation of Higgs to BB bar channel right now. As far as the discrimination is concerned, I do know that more statistics is available right now.
Yeah.
Am I clear? In my question.
The audio is cutting out enough that I'm having a little bit of I hear 80% of what you're saying, but then some of it I'm missing. So I'm kind of a little bit uncertain specifically what the question is.
Okay, maybe I'll write you on, and then from there we'll take.
Okay. Yeah, no, I'm happy to follow up. But certainly, machine learning was used, a bit at the time, and has been used more and more, and there are more and more ideas there. So if your point is just that you want me to acknowledge that machine learning has been and is being used, absolutely, I agree.
No, with it's not about it's not about the acknowledgement. It's about whether the technique is used or at what level it has been used, because this is a combined. Okay. It's a combined. Finally, eventually, the claim should be made only if it is consistent with all the available options, right? ROOFIT and RooStat, this is one way of doing it, and then multivariate analysis also is another way of doing it, right? Isn't it?
Yeah, I think that. I don't have anything prepared in terms of what the state of the art is in terms of Okay, but we can follow up and look. Sure. Certainly these things are being used, and some of the most recent ideas are only just now starting to be published. A lot of the most recent ideas are still being done internally. Yeah. As usual. Yeah.
So how is Akira and all other people?
Oh yeah, pretty good. Yeah, I still keep in touch a bit.
Yeah, I still remember. Yeah. Okay.
Yeah. Okay. Well, I've really enjoyed this. I'm actually supposed to meet someone in about 10 minutes and I need to get there. So I might have to sign off. But I appreciate talking to you all, and thank you very much for the invitation.
Bye.
Thank you. Thank you for the
Okay,
nice
so-
talk, Kyle.
Oh,
Bye.
thank you. Yeah. Take care. Bye-bye.
Right.